I was looking at the time and think it's good time to start our scientific discussion. And today is our 11th edition. It's kindly organized by Professor Emilio Silva from the University of São Paulo. And Emilio is also one of the very first speakers of this Topology Optimization webinar series. Thank you, Emilio, and the floor is yours.
Okay, thank you, Zhen Liu. So good morning, good afternoon, good evening, or good night, depending where you are. So welcome to Top Webinar 11. Thanks for your audience. At first, I'd like to thank the organizing committee for the invitation to organize this top webinar. So today we have 5 speakers from different parts of the world. So each speaker will have about 12 minutes to make the presentation and about 3 minutes for questions and answers. So total about 15 minutes. So for the questions, you can either type your questions in the chat or simply raise your hand, turn on your mic, and then you can ask. So it's my pleasure to introduce the first speaker for today, Dr. Antônio André Novotny from the National Laboratory for Scientific Computing in Brazil. And he's going to talk about an unconventional application of topology optimization on the full waveform inversion of the seismic moment tensors. So Novotny, the floor is yours.
Okay, thank you. Can you hear me?
Yes. Yes, we can.
Okay, thank you. Okay, Emilio, thank you very much for the invitation. Actually, I am really happy to be here in this nice meeting. So as you told, I will talk about a non-conventional application of topology optimization method concerning an inverse problem in seismic. So I will present very quickly the topology derivative method and some application. Then I will focus to the main part of my talk in this inverse problem seismic. Okay, here we have a geometric domain omega. The idea is to introduce a small perturbation at an arbitrary point f x hat, perturbation of size epsilon, and we want to find an expansion of this form where psi omega epsilon is the shape functional associated to the perturbed domain, which we approximate by the shape function associated to the unperturbed domain omega, plus a first order correction term, plus a remainder. So this first order correction divided in 2 parts. One, it depends on the small parameter epsilon, and the other one depends only on quantities defined on the evaluated on the original domain. So this we recognize as the topological derivative of psi at the point x hat. So it has many applications. Just to mention a few, we have here fluid flow topology optimization, inverse problem, synthesis of metamaterials, structure topology optimization, and design of the device, and so on. So let me now show a non-standard application of these ideas. This is a joint work with Professor Guzina and Alan. Alan is a former student. So here we have an elastic body clumped somewhere with a free boundary, and there is some microfolds occurring in time, denoted by F star, and we assume that we can measure the displacement on the boundary. We have access to some pointwise measurement of the displacement, okay, on this gamma m. So the inverse problems read as following. We want to find F star, the set of microfolds, which is solution to this over-determined elastodynamic problem. Here, F belongs to this set C delta, which is a complex valued function, which is written in the form of a summation of a number n of dipoles with center at xi. And this tensor M, it's a second order tensor symmetric, it's the so-called moment tensor, which represents the nature of the fault we are looking for. So find the solution to this inverse problem means find the number of microfaults, their location, and their nature. Okay. The main quantity here is this tensor M, so we want to reconstruct a tensor quantity from boundary measurements, okay? Since this problem is overdetermined, the idea is to rewrite it as a optimization problem, or we want to minimize the misfit between the boundary measurement we start and use solution to this elastodynamic system, okay? So the first step is to perturb the source by introducing a number n of microfaults or dipoles in this way. So we have the perturbed content part of the cost functional written here. So from these elements, we can develop the Ju delta in this way, where A and B are the real and imaginary parts of the moment tensor, and PKL are solution to this set of canonical elastodynamic system. Canonical in the sense that it does depend on the main unknown, the tensor M. Okay, since this tensor is symmetric, we can write in a vector form as standard. And then we can write the expansion in this compact form. So here, alpha and beta are the main unknowns, the real and imaginary part of tensor M, and psi is the set of location, also unknown. So note that we have a quadratic form with respect to alpha and beta. J and H can be seen as the topological gradients. Capital H is a kind of Hessian matrix in infinite dimension. And what is important here is that this expansion has no remaining. So it's exact up to the second order term. And we can prove that it's a strictly convex quadratic form. So minimize this, this variation with respect to the unknowns. It's a trivial step now. So let me present some numerical examples. Here we have three kinds of faults: cavitation, crack in model 1 opening, and a crack in model 2 opening. This is just a graphical representation, what I will use in the numerics, okay? So here we have a block of rock clumped here with some micro events occurring in time. And we have some sensor on the boundary when we can measure the point-wise displacement, okay? So in the first example, we have here one microfault. In red is the target, in blue, the reconstruction. This has been reconstructed with a pair of sources. This is real and imaginary part of the reconstruction. So the reconstruction is exact because there is no remaining of the expansion, okay? If we have no noise. So if we want to reconstruct two microfaults occurring overlapping time, it means that they are occurring at the same time. It's possible by using two pairs of sensors. Okay, and so on. If we want to reconstruct three faults of different nature, we need three pairs of sensors. This is not proved, but it's what we observe from the numerics, okay? So now let's add some noise. The idea here is to corrupt the material properties of the background with white Gaussian noise in this way. And then if we have no noise, the reconstruct is exact again, of course. And here n is the number of trial faults. So we are looking for two faults and we find only one. And the second one is very, very small. If we add some noise, 10% of noise, we can see a small artifact here, which is the second fault we are looking for. If we increase a little bit more, the noise up to 20%, we observe a good reconstruction and a small artifact here, okay? And finally, if we go up to 50% of noise, we observe a degradation of the reconstruction and a second fault, which is spurious. So we can say that with this level of noise, the reconstruction fails. Okay. So now we can reconstruct the three simultaneous faults of different natures here with noise, 20% of noise. The reconstruction is quite good. But if you increase the level of noise a little bit more, we can see some degradation of the reconstruction. For example, this one, the location is missing, okay? So as conclusion, I would like to say that this is a non-standard application of a topology optimization problem in geophysics, where we are trying to reconstruct a dipole, okay? And we land in a second-order algorithm, which is non-iterative. And because of that, it's quite robust with respect to noise. So thank you very much for the attention.
Okay, so thank you, Novotny. So I can open the floor for questions here. Let's see. Okay, so I will start here with a question. So in this seismic inversion algorithms, it's very important, the scalability, right? So if you have larger computational models and so on. So what you can say about the computational cost and how possible is to scale these to large models? So.
It's a good question, actually. We assume that there are some micro faults occurring at the same time. This is new, actually. Normally, what we can find in literature is that they find only one anomaly pair for each time. So the number of anomalies is quite important, but in this case, assuming that they are overlapping time, it's already some improvement. But concerning the complexity of the algorithm, let me explain quickly. So if you remember, we get this expansion. So as I told, we can trivially minimize this with respect to alpha and beta. Then we get two linear systems to solve with the size of this linear system. For example, for one anomaly is 3 by 3, for two anomalies 6 by 6, and so on. And then once we get solution, we come back to the expansion, and then we have to find the optimal location solution to this combinatorial problem. This is the bottleneck of the algorithm. Okay, so once we solve this, the solution is the pair of optimal location and optimal component of the moment tensor. And this we have to solve in a set of admissible location capital X. So it strongly depends on the cardinality of X. So in order to explain better, the complexity of the algorithm can be estimated in this way, where M is the cardinality of the set of admissible location, and N, capital N, is the number of trial folds. Okay, so we get this approximation. Graphically, we can see here, if you, for example, let's fix here in the red line, where we have the cardinality, it's 400 points at the domain. So if N is small, the complexity is small. We are here. And if the N is comparable to M, we are in the other side, so the complexity is also small. I mean, there's no combination to test. However, if N is more or less half of capital M, we are in trouble. So the complexity really increases crazily. So the idea here in this work, I work in this region where N is quite small in comparison with M, that's all. Okay, so we have like 3 anomalies, but this runs in a few seconds. Okay, it's very quick. Okay.
Okay, so it's about 15 minutes here. So thank you, André. So then later we have opportunities for more questions if someone has. Now I'd like to move to the next speaker. So I'd like to invite Professor Liang Xia from the Huazhong University of Science and Technology in China. He's going to talk about data-driven design approach to hierarchical hybrid structures with multiple lattice configurations. Okay, Liang, the floor is yours.
Can you see my screen?
Yep.
Okay, good. Hello, everyone. My name is Liang Xia from Huazhong University of Science and Technology. And first of all, thanks a lot for the kind invitation from Professor Silva, and also to all the organizers of this platform. Today, I'm going to share with you our recent work on hierarchical data-driven design of hierarchical hybrid lattice structures. So this work was published last year in 2020 in SMO, which is actually an extension of our earlier work published in 2019 in CMAME. So as we all know, 3D printing has enormously improved the manufacturability, and complex and hierarchical structures made of elegant graded lattices can now be fabricated without much difficulty. And so a lot of research has been conducted on these design methods to achieve this kind of design, including topology optimization. Here, I just borrowed the nice design image from the work of Dr. Ling Chen at Pittsburgh to illustrate this idea. And by looking at this graded lattice bracket, it reminds me of the seminal work of the homogenization method to topology optimization. But the topology optimization assumes separation of scales. So this is the key difference of these two works. By the homogenization work, the cells here, the sizes are infinitesimally small compared to the structure. But for truly fabricated structure lattices like this, they do have specific sizes. So this is the discrepancy, especially when design a lattice with homogenization assumption, discrepancy happens between design, the performance of design, and the fabrication. This is a typical design flow to achieve graded lattices. Usually with a specific lattice, we can estimate its equivalent constitutive behavior by homogenization and interpolation of constitutive coefficients. With this material array model, we can perform standard density-based topology optimization to have a density field or density distribution or size variation field. But finally, this density distribution needs to be further interpreted into fabricable lattices. And this is where the issue arises because homogenization assumes infinitesimally small lattices. So what I mentioned, the discrepancy between design and fabrication. And to our knowledge, this is this design flow has become a very popular industry and has also been adopted in a lot of design software. So to avoid this discrepancy, we came to this idea of doing substructuring instead of homogenization. The idea here is that we can still assume a density variable which is linked to the geometry of lattice to control the square hole, as was also did in conventional homogenization. But here, the design domain is discretized into subdomains or lattice cells with specific sizes. So by doing so, we no longer need to establish a model to link density and the Young's modulus, but to parameterize directly the stiffness matrix of lattice cell. And obviously, a lot of to do this parameterization, there are a lot of ways to do it. In this work, considering the fact that a lot of similar or even identical lattices are repetitively used in design, here in our work, we condense these lattice substructures into superelements by static condensation. This is a mature operation in linear finite element analysis to reduce computational cost in simulating structures made of identical modules. And here, one thing need to be mentioned that this operation does not introduce any loss of simulation accuracy. And now the constitutive behavior of a lattice is governed by this superelement stiffness matrix. By changing the density, we can sample a series of different superelements. So we have a lot of different stiffness matrices. With these matrices, we can establish a surrogate model by means of proper orthogonal decomposition and interpolation of projection coefficients to provide an analytical expression of this reduced stiffness matrix in terms of this density variable. Here, phi 1 to phi m are the eigenmodes or common features of these stiffness matrices extracted by the proper orthogonal decomposition. Once this expression is established, we can derive analytical sensitivities, and thereafter topology optimization or size optimization can be straightforwardly performed following a standard design procedure. Of course, this model can be extended to consider multiple lattice configurations. Here we need two types of design variables. One is X, a discrete variable indicates the type of lattice configuration, and another continuous variable or density variable governs the geometry or the density of lattice. And notice that to favor gradient-based algorithm like MMA, the discrete variable X is in fact a heaviside projection from a continuous variable S, which is bounded between 0 and 1. And finally, with X and Y, two types of design variables defined, we can define a multi-material interpolation model, which is basically the same as we did in multi-material topology optimization. The only difference here is the interpolation is operated on stiffness matrix instead of Young's modulus. Now we take a look at an example cantilever beam compliance minimization problem. We consider two types of lattices. Both lattices have a square frame, one with a square hole, another with cross trusses. And by changing this geometry parameter T, we can change the lattice geometry and the density. Each of the lattice is discretized into 120 by 120 square elements. Notice that we did not use truss or beam elements, which means actually the lattice, the geometry can be arbitrary, not necessary to be truss-like lattices. 3 discretizations have been considered in this design, and obviously the discretization influences the design, as the mesh is refined, you can see the topology converges to a similar topology. The design converges to a similar topology. And the lattices with square holes, they can lead automatically to a very clear design with compact structure configuration. However, when the other lattice type is considered, we can see there are a lot of lattices with intermediate densities. This is very similar to those density-based designs when the penalty parameter is set as 1. But the thing is here, these intermediate densities, these lattices, they are physically clear and they can be fabricated or sent for 3D printing and with little sacrifice of the design performance. If we want to reduce the complexity of the structure, we can simply including a penalization term before the stiffness matrix. Here we can see by increasing this penalty, we have clearer design, which is similar to conventional solid material design result. Of course, the compliance is increased due to this penalization. Actually, here we have a very interesting conclusion is that if the type and the size of the lattice is fixed like this one, then lattice design with a lot of intermediate densities, actually it outperforms than pure solid material design in terms of compliance. In my opinion, it provides a very interesting perspective on the advantages of doing multi-scale or hierarchical designs. Then with the multi-material interpolation, we can consider multiple lattice configurations. Here we consider 4 additional lattices with the directional enhanced stiffness together with the previous 2 lattices. The results are rather convincing, and not surprisingly, the compliance is reduced if more candidate lattice types are considered in design. In this table, we list the detailed percentage of each lattice type in design. In the first design, we consider only M1 and M2 types lattices. And we can see the design is dominantly consisted with M6 lattice, for it has superior performance in bearing shear load. However, when 6 lattice types are considered in design, you can see M1 type lattices are mainly replaced by M2 lattices whose horizontal stiffness is enhanced. Another interesting observation is that in the second design, even though M4 lattice type is included in design, but it is excluded from the final design completely. And here are some 3-dimensional designs with considering 2 lattice types, and similar observations can be drawn as from those 2-dimensional designs. A very interesting extension of this work is to thermoelastic designs. Here we still consider 6 lattice types, and the density variable is bounded between 5% to 95% for visualization purpose to show which lattice type it is. And when only mechanical load is applied, all design variables attain their upper bound, and the result is very similar to conventional solid material topology optimization result. However, when the temperature load is applied, especially the temperature load is high, you can see porous lattices are much more preferred in design. The same problem has also been designed for comparison using density-based method. You can see when the temperature load is set as high as 60, there are a lot of green materials in design, even with standard the penalization on the Young's modulus. Of course, we can further restrict the design to drive it to more clearer black and white design, but the performance we can see is severely sacrificed. However, for lattice design, the performance is the same competent, but these porous lattices, they are physically interpretable and can be sent directly for fabrication. And another interesting finding is that when thermal load is included in design, actually for a design with similar performance, we don't need to have such a fine discretization. Similar design result with the similar compliance actually can be achieved with coarser discretization, which means many less design variables. So finally, by this work, actually, we just proposed an alternative approach to lattice topology optimization, where the scales are not separated and the designs are physically interpretable and fabricable. And in our opinion, there are a lot of interesting and challenging extensions can be done within this framework. And that's all of my presentation. Thank you very much for your attention.
Thank you, Professor Shi. So I open floor for questions. Okay, so I just, okay, so someone wants to ask. Oh, Oli, how are you doing?
Yes.
Sorry, you can, sorry, okay.
Okay, thank you for the talk. I was wondering about the CPU time here, because you have less degrees of freedom in your finite element problem, but on the other hand, you must have quite large bandwidth. So how much CPU time compared to a full-scale analysis do you spend here?
Actually, we did not do a very strict comparison between for the CPU time for this, but we sure that for the finite element analysis part, by substructuring, we can increase a lot of the speed.
Really, but don't you have a very big bandwidth of your stiffness matrix?
Yes, that's true.
But that doesn't cost.
It costs, but considering the degrees of freedom, we have been saved from the static condensation part, because like it's 121 by 100 square elements, and then finally only the boundary nodes, those degrees of freedom are retained in our design.
Okay.
Okay, so I have two questions from Karin and also News Age. So I think Karin raised the hand first, and so okay, you can.
Yes, thank you for your presentation. It was very interesting. I have a short question about the reduction that you proposed. So you mentioned the use of the POD methods, which involves the eigenmodes, as you mentioned. So, but does it also mean that during the sensitivity analysis, you need to compute at each time the derivatives of the eigenmodes with respect to the design variables? And doesn't that also take a huge amount of computational time then?
No. Can you see this screen, the page 6?
Excuse me?
Yeah, you can see page 6.
Page 6.
Yeah,
yes,
we can see. Yeah.
These eigenmodes, they are fixed. They are pre-calculated. So they are fixed during our simulation. Only interpolation is done for these coefficients. So for these, the
you pre-compute them.
Yeah, the modes are fixed, are pre-calculated beforehand.
Okay. Jun, you want to ask some question or?
Yes, Shana, I have a question about slides page 10. On page 10, you made a comparison between these 3 different designs. I'm wondering, when you do this comparison of the compliance, which stiffness matrix you use? Does the stiffness matrix also depends on the penalty term you used?
Yes.
So they are evaluated with different stiffness interpretation of the same density value.
Yeah, that's true. Yeah, when P is 1, actually, this one is the exact result. When P is 2, yes, I didn't think about it. Yeah, because I thought all variables, they attend almost to the upper bound. So, but it's different. Yeah, it's not almost, it's exact 1. Yeah.
I think also would be interesting to simulate the structure in the full resolution and that would be a fair comparison, in my opinion. Yeah,
but the linear, because for static condensation, it does not introduce any simulation error. But I will check if this result is if this is the exact result or it is a penalized result. But because it's 2 years ago, I didn't remember very details.
Thanks.
Okay.
Yeah. Thank you for the question.
Thank you. There are 2 questions here, but we are beyond 15 minutes here, so I believe that they can ask these questions at the end, right, Jungwoo? Right?
Yeah.
Okay. So I will move to the next speaker here. Okay. So the next speaker is Professor José Carlos Bellido Guerrero. He's from University of Castilla-La Mancha, Spain, and he's going to talk about density-based topology optimization consider nonlinear electromechanics. Okay, José, the floor is yours.
Thank you very much, Emilio. Okay, you see the screen. This is a joint work with Rogelio Ortigosa. Well, first of all, I would like to thank Emilio for the invitation, for taking part in this session, and the rest of organizers of the talk webinar. This is a joint work with Rogelio Ortigosa and Jesús Martinez-Frutos from Cartagena in Spain, and my colleagues in Castilla-La Mancha, David Ruiz and Alberto Donoso. And this is going to appear in SNO soon, I guess. Well, we are concerned with electroactive polymers, which is now a very intense area of research within the framework of smart materials. Particularly, we are interested in dielectric-elastomers and piezoelectric polymers. Dielectric-elastomers are a material which experiment electrical induced deformation, moderate or large deformation, and additionally have very low stiffness. So those are suitable for many applications, assault robots, deformable lenses, and so on. On the other hand, piezoelectric polymers also experiment electrical induced large deformation. Contrary to dielectric-elastomer, they have much larger stiffness and also a reciprocal effect. So under an electrical charge, they experiment deformation and the other way around. So if we apply a mechanical stress, we obtain electrical charge. So those are suitable for actuators and sensors. And for many applications like energy harvester or acoustic transducers. So topology optimization opens up a very interesting field for optimizing this material in order to design devices beyond human intuition. So our aim here is to design a density-based topology optimization approach in the context of electromechanics. We consider a model both for a dielectric-elastomer and a piezoelectric polymer model. And because we are going to have large deformation, electrical induced deformation, we have to go through nonlinear modeling, particularly finite elasticity modeling. And this is a multi-physics problem in which equilibrium is obtained as the solution of a coupled system of nonlinear PDEs. So going into the modeling, starting with nonlinear mechanics, so we always have a reference configuration, typically called B0, and a deformed configuration, which is the configuration that we obtain after applying charges. And the relevant magnitude here is the deformation, its gradient, that here I call F. So this is the deformation gradient, and there are another two relevant magnitudes, which are the cofactor of the deformation gradient, this H, and its Jacobian, the Jacobian of the deformation gradient. So these are highly nonlinear quantities, depending on the deformation gradient, because those involve the determinant. So the elastic equilibrium is obtained as the solution of this equation, where this Pf0 is the distributive force, and then we have a traction force, we have a Dirichlet boundary condition, for instance, if the structure is anchorage, and this P is the first Payola-Kirchhoff stress tensor. Then we need a constitutive law for obtaining this tensor from the deformation gradient. For the electrical part, we have two laws involved, the Gauss law and Faraday's law. Gauss law determines the electric displacement given the electric volumetric charge and the boundary charge. And Faraday's law establishes that the electric field is obtained as the gradient of a scalar potential. So we need a constitutive equation. There are two ways to do this. We have used the Helmholtz functional. This is representing energy functional per undeformed volume, and it depends on the variables in the reference configuration X, the deformation gradient, and the electric field. Once we have defined the Helmholtz functional, then the first Payola Kirchhoff stress tensor is obtained as the derivatives with respect to f of this functional, and the electric displacement is obtained as the minus the derivatives with respect to the electric field. So with this relation here and the previous equilibrium, we have the system of nonlinear PDEs for obtaining equilibrium for this electromechanics model, but we need a constitutive relation. First of all, for solving this, we are going to work with large deformation, but in the, let's say, moderate range of nonlinearity. So we can do it with Newton-Raphson, the finite element analysis. And now we have to choose for each model the concrete Helmholtz functional. For instance, for the dielectric-elastomer, we have two contributions, one purely mechanical and electromechanical one. For the purely mechanical, we use the typical modeling hyperelasticity, Munich-Rilling. And for the electromechanical one, we use this quadratic functional in here, involving the cofactor of the deformation matrix and the electric field. This dot here means a scalar product, so it's again nonlinear. For the, well, all the parameters in the Munich-Rilling can be related to Poisson ratio and Young's modulus, and epsilon 0 is the electric permittivity of vacuum, and epsilon r, the electric permittivity, relative electric permittivity. The model for the piezoelectric polymer is a bit more complex. We have also a new ingredient, which is this V. This is the polarization direction, and the electromechanical part have the electric contribution and the piezoelectric contribution. With all these parameters, we can characterize completely the piezoelectric tensor of the material. And the mechanical contribution is also more involved due to this polarization direction. Well, this is the modeling, and now we have a typical topology optimization problem for the design of an actuator. We want to maximize the displacement in a certain direction given by L0, and this phi is the deformation. So we consider the Helmholtz energy function given the constitutive model, and now we have a discrete function taking value 0 or 1 for differentiated between solid and void regions and the typical volume constraints. So this is a typical topology optimization problem for designing an actuator, but with this nonlinear modeling of electromechanics. We use the SIM approach, so all the ingredients of the SIM approach are present. We pass from a binary discrete dense variable to a density, taking values between 0 and 1. We use density filtering as usual, also density projection for having a physical density. And now we have to define an interpolated strain energy density, and this is probably the new ingredient in this work because of the nonlinear modeling. So we do this dehomogenize Helmholtz functional in the following way. This is something that we somehow propose and check how it works. So we use the same idea of the same method for linear elasticity. So exactly the same. We use penalization. But two different penalization for the mechanical and the electromechanical part with different exponents in principle. So we have Pn, which is the penalization of the purely mechanical part, and Pe, which is the penalization for the electromechanical contribution. So doing numerical experiments to determine the influence of these parameters, Pn and Pe, seems to us something of major importance. And we will see that we have interesting results in this sense. So it's worthy to mention about the modeling of void. So we model void as a quadratic linear functional in the mechanical contribution. So typically this C0 is the elasticity tensor corresponding to the nonlinear mechanical model at the origin. So for deformation or deformation gradient equal to identity. And for the electromechanical part, we consider this is in the dielectric case, we consider the electromechanical contribution evaluating again at the origin, because this we have checked that this is more convenient for avoiding instability due to low and intermediate density values. Well, first example is for a dielectric-elastomer. We have a host layer, which is not optimized, an active layer. That's what we optimize. We apply an increment of potential. And then we will see some results here, for instance. We consider Pn equal to 3 just because it's the usual value that it is used in elasticity for the SIM methods. And then here we see this ratio between the Pe and Pn. So Pe is always bigger or equal than Pn because we have checked that when P is smaller, the algorithm doesn't work. So here we see the designs, the form, the deformation as well. And here we see a picture, black and white, of the design. We see that as we increase this ratio, gray disappear. We have some gray areas for ratio equal 1 in here, but it disappears until we get this ratio equal to 2. So it seems convenient, at least in this example, to increase this ratio. This is just a dielectric-elastomer based gripper. If we increment the potential, we get this effect, putting together 4 of those devices, design devices. Now we see an example for a piezoelectric polymer actuator. We have now a host layer and 2 layers in phase in order to get displacement, out of plane displacement, so bending. Well, just to differentiate from the previous example, I have chosen to take Pn equal 5. And again, we see more or less the same effect, very little gray, but still gray for ratio between Pe and Pn equal 1. And then when we increase that ratio, then gray area disappear. Of course, deformation is smaller, but still this is real deformation. And finally, we have a multi-layer torsional piezoelectric actuator example, when we have again a host layer and we have optimized several layers, actuated layer, one on top of the other, and we have the ratio between Pe and Pn equal 2 again. It works out very well as well. So just to end, conclusions, then we have implemented a density-based topology optimization in the context of electromechanics, focusing on dielectric-elastomer and piezoelectric polymers, in which we have large electrical induced deformations, and we have to use nonlinear modeling. We have used an energy interpolation scheme between solid and void regions that have shown to be successful for preventing numerical instability associated to this kind of problems due to low and intermediate densities. And in view of numerical simulation, it is strongly advised to use Pe strictly bigger than Pn, in opposition with linear piezoelectricity, where non-penalization for the electromechanical part is required, actually. Then this is all, and thank you very much.
Thank you, Bellido. So I will open the floor for questions. Okay, I have a question, right, regarding the sensitivity of your formulation. So are you considering the non-linearities, or you are doing an approximation, or you calculate exactly the sensitivities?
No, the sensitivity is are calculated exactly, actually, using the nonlinear model. the resolution, so the numerical resolution of the equilibrium is done by sequential linearization, so by Newton-Raphson. But sensitivities are calculated directly.
Okay. Okay, and also regarding your void, right?
Yeah.
The property there is small enough to be considered a void because you have these high deformations and so on, and then.
Well, we think so. That was a question of the referees, but we think so actually. I don't know what to say about that.
Okay. So, is there anyone else who want to ask a question? I don't see anyone here. Okay. Thank you, Bellido. So it's about time to move to the next speaker. So I'd like now to invite Professor Peter Dunning from University of Aberdeen, United Kingdom, and he's going to talk about a review on feature mapping methods for structure optimization. So Peter, the floor is yours.
Okay, hello everyone. Thank you for the invitation to speak at this webinar. So I'm going to talk about feature mapping, which is a term that we came up with during a recent review that I did with Dr. Fabian Vine and Professor Julian Norato. And the review was recently published in SMO. So in this presentation, I'm going to talk about the motivation for our review, talk about what feature mapping is, its definition, some of the numerical issues involved with feature mapping, a few applications, and then a future outlook on research directions for feature mapping methods. Okay, so what was our motivation? Well, we'd noticed that there were quite a few methods that have been developed recently that had some similar characteristics, particularly in the numerical implementation and the numerical challenges that those methods had to overcome. And we wanted to do a review of these similar numerical challenges and the different solutions that have been proposed in the literature. But first of all, we had to decide what the scope of our review was, and we ended up looking at these two different aspects here. So along the top, we have geometry parameterization, and we wanted to look at methods that had some kind of high level or restricted geometry parameterization, opposed to the more kind of low level or verbose parameterization associated with traditional topology optimization techniques, such as SIMP or level set. And the reason that these methods come up with this is to somehow gain more control over the geometry in the final design. And the other aspect we looked at was the analysis mesh itself. So all these methods were using some fixed or unfitted mesh, opposed to some methods that have been developed where you have a fitted or moving mesh. And one of the main reasons for that is they wanted to avoid issues with remeshing or having to deal with a moving mesh, which is quite complex. So we wanted to focus our review on methods up in the right-hand corner here. And this then gives us our definition for feature mapping. So we define feature mapping as having these two essential ingredients. You have a high-level geometry description, which is then mapped onto an unfitted mesh. Now, this unfitted mesh is usually a fixed mesh. So sometimes I use the term fixed mesh, but it means the same thing. So now I'm going to look at some of the numerical challenges involved with doing this. So the first challenge you would come up with is, how do you map a single feature, such as a hole or a structural component, onto a fixed mesh? And there are two main ways of doing this in the literature. One is to use pseudo-densities, and the other to use immersed boundary techniques, such as the extended finite element method. And essentially, both of them are doing a similar job. They're taking the volume integral over the structure here, little omega. So this is just some functional that we're trying to integrate. And instead of integrating it over the structure, we're integrating it over a bigger domain. And we modify that with an indicator function where 1 is inside the structure and 0 is outside the structure. So in pseudo-density approaches, this is approximated by calculating usually an element constant pseudo-density value, or relative density between 0 and 1, and that modifies the volume integral within each element. Note that the pseudo-density is often further modified using material interpolation schemes such as simple power law or something else. For most boundary techniques, It's simply then just integrating over the part of the element that's inside the structure. So what are the numerical issues involved with these two different approaches? So let's start with pseudodensities. So one of the first challenges is that if we want to calculate an element constant pseudodensity, we need to integrate this indicator function. But this indicator function is non-smooth. So this is often replaced with what's called a smoothed Heaviside function. And this means we also have to come up with another function here, which is a scalar indicator function, which tells us whether we're inside or outside the structure or on the boundary. So this is very similar to a level set function. So now that we've done this, this is nice and smooth and differentiable. We have an analytical derivative here, but often this is evaluated using some numerical integration scheme in methods. And often a normal choice in the literature is to evaluate this smooth Heaviside function at just the center of the element. So using a one-point numerical integration scheme. There's a study in the review paper that shows that there may be benefits of using higher order numerical integration schemes. So if you're doing pseudo-density feature mapping, there are 4 ingredients you need to think about: the form of the material interpolation function, such as simp, the form of the implicit function, and we recommend in the review and in other places in the literature that a sign distance function is used, because that means that the transition between structure and void around the boundary of your structure is the same everywhere. It's got the same gradient, and that helps with convergence and things like that. The form of the smooth Heaviside function, there are different ones used in the literature, such as polynomials, and the numerical integration scheme you use. Okay, so now let's look at immersed boundary techniques. So there are some numerical issues you need to think about here as well. So one of the main benefits of doing immersed boundary is it captures the geometry of the boundary more accurately. But that can result in things like non-physical coupling. So if we've got 2 components here, and this is my element, then I need to make sure that my enrichment functions capture the fact that these 2 components are not actually physically coupled. You can have islands of material as well, which you need to deal with. And there are also potentially issues with small integration areas, especially if you're using an iterative solver, and it can cause issues with accuracy of stresses as well. So the numerical ingredients are the enrichment scheme you use to model the interface here, interface conditions, which are often ignored for a solid void interface, but if you have a material-material interface, then you need to ensure some sort of continuity across the interface. And again, numerical integration scheme used to integrate just over the domain of the element inside the structure. One of the main challenges with this is the sensitivity calculation. So for pseudodensities, sensitivity calculation is usually straightforward. You can use a chain rule and everything is nice and easy to work out. But for immersed boundary techniques, there is a challenge. So there's 3 main ways people have done this in the literature. One is to differentiate and then discretize. So use something like a shape derivative or a topological derivative, and then calculate that in the discrete system to drive the optimization. Semi-analytical approaches where, say, you use a finite difference to work out the change in, for example, the stiffness matrix with a small change in your design parameters, such as the position of your components. This has some issues, so there's also some recent approaches looking at a full analytical approach, which are more complex, but they do avoid some of the issues with the semi-analytical approaches. Okay, so now you can map a single feature to your unfitted mesh. To be able to do topology optimization, you need to be able to map multiple features. You need to be able to combine them together. And again, there are various ways of doing this in the literature, and the way that we classify and categorize them is the order in which operations are done. So here I show what we called combine then map approaches. So if I start with these 3 solid components here, modeled using splines, I could combine them into a single spline. I then convert that to a sign distance function. This is my smooth Heaviside and the density field. I could also map each separate component to a sign distance field, and then I could use something like a smooth maximum function to combine these together and then go through the same process. Now you notice that there's a subtle difference between the left and right here, but the pseudo-density field that you end up with looks different. So the order in which you do these operations does matter. There's also what we call map then combine. So this is where you map each individual feature to a separate density field. So this is more for density-based feature mapping. And then you combine the density fields together using something like a smooth maximum function. One of the additional benefits of doing it like this is you can further penalize each individual density field to be able to remove components from the design. So this is shown here for the diagonal member. So here we got what's called a penalized size variable of 1, and that's decreased down to 0. And you can see that that diagonal member disappears from the design. One of the issues in the literature that has been observed is local minima. When you're doing topology optimization with feature mapping, you can often get very different designs if you start with your features in different starting positions. And we came up with a simple test case to show this. So it's a simple 4-bar example here. And we only have one design variable, which is the position of this bar here. And if you plot the compliance of this structure by moving this bar up and down, you can see that you get two distinct local minima. Now, if I start with the bar here, I end up in the poor local minima. If I start with the bar near at the top, I'd end up with the global minimum. There's not been a lot of work done on this. There's been some work, and I think this is one of the interesting future research directions, is how to improve this situation, if not completely solve it, for feature mapping topology optimization. Just want to briefly mention hybrid methods. So this is where you combine feature mapping with some freeform topology, which we included in the review as well, to achieve things like engineering feature control. There's been a lot of work on embedding solid components in freeform topology, and this is just one example. And I like this example here because here the components are actually functional. So these red boxes are actually actuators providing a force for this compliant mechanism, and their location and orientation is part of the design space. So just a brief look at a few applications of feature mapping. So you can build components out of stock material like plate structures, thermofluid problems, material design such as lattice materials, phononic band gaps. So here the feature mapping has been used to ensure continuity of the material, which is important. Multi-material, so here each of the components has a different material, which is easily controlled using a feature mapping approach. And then classical things like compliant mechanisms. So in conclusion then, feature mapping we define as methods that have a high-level geometric parameterization, which you can think of as the features, which are then mapped to an unfitted mesh. Some recommendations for future research that came out of the review, I've talked about local minima already. As always, when methods start, they solve classic compliance minimization problems, etc. But it'd be good to see more applications to problems that are not so easily solved by traditional topology optimization methods, because that's where the real power of these things comes from. Use of complex features. So I've seen some recent work where you have tubular components for topology optimization and coated components, so more complex components being used. One of the claims is that doing this enables a more direct link to CAD, so it'd be good to see some more work demonstrating that. And it's theorized that you could even have components with different functions in physics, but again, there's not much evidence of that in the literature, so it'd be good to see some work along those lines. So thank you for listening, and I'm happy to take any questions.
Thank you, Peter. So I'm opening the floor for questions. Oh, Jung-Woo, okay.
Yes, I have a question about so what is the biggest benefit regarding computational complexity from this geometry mapping approach? My understanding is the computational complexity is directly connected to the mesh resolution. So on this aspect, does geometry mapping increase computational performance?
I think it depends on, one of the benefits is that your design space is smaller, okay, because you have a high level geometric parameterization. And that has even enabled some people to use things like genetic algorithms to solve very complex problems. Mesh resolution is an interesting thing. So typically you'd actually want more resolution around the boundary of your structure to more accurately capture it, and less resolution away from it. So there's been some work in the literature recently looking at multi-resolution type approaches to keep the accuracy without making the computational cost too large.
Okay, thanks.
Okay, next question is from Niels.
Thank you very much for the presentation. I want to
your mic, yeah, it's too high. I mean, the volume looks like it's too high. And then,
thank you. Is this better, Emilio?
yeah, now it's better. Yeah.
Good, good. No reason to shout at anybody. No, thank you, Peter, for your presentation. I have a question regarding shadowing. So if you have multiple entities moving around in your mesh, you can often come into situations where two or several entities will overshadow a third one. Is this something you have looked into, and do you have some good suggestions for how to treat these problems? When it's completely covered, meaning that the design sensitivities end up becoming zero.
Yes, so that's all down to how you achieve this, how you combine the features together, and what operations you do to actually combine them. So I would say that if you're using something like a smooth maximum function, then you will retain some sensitivity. Okay, yeah. Depending exactly how it's done, right? But I do agree with you. This is another potential issue. Is like if one component is completely enclosed inside another, then it doesn't know where to go.
No,
because it doesn't really have any real sensitivity information. Perhaps that's part of exploring that problem in more detail. Maybe could lead to more ideas and solutions of how to, at least not completely solve, make the problem of local minima better. Right. So maybe that's one aspect that could be looked at. That's a good suggestion.
No, thank you. Definitely interesting. So thank you very much.
Okay. So anyone else has a question? Someone raised the hand. Pichelli, yeah, please, Renato.
Yes, thank you, Peter. Very nice, thorough review. Do you see any particular challenge or issue in extending these methods to multiphysics problems? As you mentioned, you haven't seen many of them applied to other physics.
Yes, so there is this recent one from you et al. I don't know if this would be, I mean, you can go look at the review paper for the full list of references and everything, but so this was a thermofluid problem, and they managed that without any problem. I think in my kind of recommendations is that if you had different components with different functionalities and different physics, that might lead to some interesting applications. I'm not sure what the challenges may be. I guess you'd actually then have to have some way of adapting your numerical solution so that in some part it was following some model and in another part it was following a different model, and how that was coupled together. But yeah, this would be something interesting to research in the future.
Okay.
Okay, thanks.
Okay, so thank you, Peter. So let's move to the next speaker now. So next speaker is Professor Daniel Milbrat de Leon from Federal University of Rio Grande do Sul, Brazil. He's going to talk about stress-based topology optimization of compliant mechanisms design using geometrical and material nonlinearities. So Daniel, the floor is yours.
Okay, thank you, Emilio. My screen.
Yeah,
okay.
It's okay. It's okay. Everything is okay. Yeah.
Just. Okay. Okay. First of all, thank you, Emilio, for inviting me to this top webinar. Let me introduce myself to the audience. My name is Daniel de Leon. I'm from Federal University of Rio Grande do Sul in Brazil. This work was done together with Juliano Gonçalves from University of São Paulo and Professor Carlos Eduardo de Souza from Federal University of Santa Maria in Brazil. This work is titled Stress-Based Topology Optimization of Compliant Mechanisms Designed Using Geometrical and Material Nonlinearities. The main goal, strictly speaking, the main goal of this research is to study the influence of the nonlinear material in stress-based problems in compliant mechanisms of light displacement. There are a couple of works dealing with nonlinear materials for geometrical nonlinear problems, but looking for the stabilization of the problem. Most of all using Newton-Raphson schemes. So Newton-Raphson schemes sometimes lose the path of convergence in topology optimization of large displacements. And but there are just a few works dealing with nonlinear materials in stress-based problems, and we think this investigation for compliant mechanisms was done for the first time. I'll try my best to differentiate between linear and nonlinear materials and linear and nonlinear equilibrium in the examples that I'll show to you. I think I'll get success, but in this presentation, I'll show to you just one benchmark problem for the sake of brevity, but in the original paper, there are more benchmark problems, and the methodology applied here was applied for more benchmarks. Okay, so we are using here the material nonlinear is an Hookean model. It's as in equation 1. It's a polyconvex model. It's very long, and it was not applied for the first time in this work. It's commonly applied for nonlinear materials in topology optimization. C is the right Cauchy-Green tensor, J is the Jacobian of the deformation gradient, and G is the Green-Lagrange deformation tensor. The stress we get here from this stored strain energy equation 1 is the second Payola-Kirchhoff, and if you differentiate twice, we obtain the tangent constitutive equation that is used in the Newton-Raphson scheme. And equation 3 is the classical SIMP method that uses material interpolation scheme. Okay, the optimization problem applied in this work is the classical formulation for compliant mechanisms is trying to maximize the output part of the mechanism. The only difference here, we replace the equilibrium equation of nonlinear problem by the residuum vector for the Newton-Raphson scheme. Sometimes when I state that we are using a linear problem for the finite element mesh, we are using the classical equilibrium equation for linear problem in finite element mesh. There's a constraint in the volume, and there's a constraint on stress that I'm going to show to you how to get this maximum stress in the next slide. Every time you see that we are dealing with stress-based problem, we are using this constraint in the problem. In order to get topology designs as sharp as possible, we are using a projection scheme, the density filter variable, equation 6. It's not the goal of this work to obtain sharp topologies, but in stress-based problems, it's important to get as sharp as possible. So we are using this equation 6, this projection scheme that's very known in literature for topology optimization problems as well. Okay, here stress. As I showed to you in this previous slide, we are obtaining the second Payola-Kirchhoff stress when we are deriving that potential, the equation 1, regarding to the deformation tensor. But the second Payola-Kirchhoff doesn't have physical meaning, so we need to need this transformation, the second Payola, to obtain the Cauchy stress. Cauchy stress has physical meaning, so we are using Cauchy stress to obtain the von Mises stress, the equivalent stress measure that we are using in this investigation. Von Mises stress obtained the non-penalized stiffness matrix. To relax that's von Mises stress, we're using a very known equation, equation 8 here, to obtain the stress, the relaxed stress that we're using here. Here in this work, we use a global P norm to measure stress or to control. We control a scalar by the global P norm, and not every point in the domain. So we have one number representing the maximum stress in the body that we obtain from this global P norm, exactly as in the work of Lee. Here we use the P equals 8 to the P norm. Then we obtain sigma Pn, and the sigma Pn is used to control the maximum stress in the mesh. Oh, here is a sketch of the inverter. This is the compliant mechanism that I'm going to show to you in the results section. That's why we are minimizing output, the output port, because the output port's in the negative direction. So we are minimizing. For others mechanisms, of course, the maximize the output ports, the more convenient formulation. So we're modeling just the lower half of the mechanism to save computational effort. It's symmetry here, and all dimensions and spring values are in the original paper, so I omitted here for the sake of brevity. Okay, our first investigation here is the following. Here, it's not, we cannot consider a stress-based problem because the stress sigma star, the limit imposed on the stress is infinite. So we do not have a stress-based problem here to begin with. So the left corner here is the mechanism, the topology design obtained using a linear formulation. Linear for the finite element mesh, non-neutral Epsilon scheme, a linear finite element mesh, and a linear material, hook law, the classical hook law. And the right is non-linear formulation. Non-linear for geometrical, using a neutral Epsilon scheme, and a non-linear material using the potential that I showed you in equation 1. So we have here there is no constrained stress, so we are just measuring stress here and here. And all the boundary conditions for both examples are exactly the same. So look, let's look to this mechanism first. Our first investigation here is we have this first line is exactly the mechanism that I showed to you here in the left corner. So what we did here, we did not perform another topology optimization problem. We just run an equilibrium analysis, changing the linear part of the finite element solution by a neutral Epsilon scheme. So we took the optimized design that we got in the left portion using a linear formulation and replaced the linear equilibrium finite element solution by a neutral Epsilon scheme to deal with geometrical nonlinear, to have a geometrical nonlinear problem of the optimized topology. So here is the objective function that we got, that the maximum stress we observed. The second portion, we took this optimized topology using a nonlinear problem and replaced the nonlinear material by a linear material. Neutral Epsilon scheme is kept here as the original problem. So what we can see here is what we see in other works in literature. We can observe that the material nonlinearity in a non-stress based problem has no prominent role in the problem of objective function of the kinematics performance of the mechanism. We can see that replacing the linear finite element solution by a neutral Epsilon scheme, keeping the linear material, we obtain a better performance. We can reach a better local minima, you can say, using a neutral Epsilon scheme. Just made the equilibrium analysis. But if you replace the nonlinear material, the polyconvex material that is applied in this work, if you replace by a linear material, the hook law, there is no difference in the output displacement kinematic of the compliant mechanism. It was discussed in a couple of works when dealing with nonlinear material. But the next step of this investigation is the following. So we can conclude from this table that a nonlinear material plays no role in for the kinematics of the compliant mechanism design. So here is the following step of this investigation. Now the constraint stress active sigma star is not infinite. Sigma star is a value that here in the left, letter A is almost inactive because the maximum stress observed in a problem without stress constraint was 4.8 giga or something like that. I don't remember very well. But 4 giga is just some elements here have the constraint active. Then we decrease this limit for sigma star slowly up to 0.9 giga, more or less. In the full paper, there are intermediate results here to observe the change in topology, but here what's interesting is that we go to this limit of 0.9 gigapascal. That's around the limit of the, I think I forgot to mention that we're using silicon as material base, so it's more or less in the limit of the strength of the silicon for this kind of problem. So now we get a very constrained topology that any element here in the domain are more than 0.9 giga. So here are the stress plots. You can see that here we have some elements, especially in the hinges, some elements are active, are 4 giga, but when we decrease the sigma star to a 0.9 giga, we have a lot of elements in the mesh that are active. So of course the kinematic of the mechanism is decreased a little because we have a constraint in the maximum stress. So now let's pay attention to this letter B here. So the idea here, the methodology here is almost the same of the first methodology. We took this line is the mechanism that is here, this topology with 0.9 giga stress, the maximum stress observed there is 0.89 giga. So we took this topology and run one analysis of finite element, not the topology optimization as a whole. We keep the finite element solution using interruption, but we change the material. We replace material, Nehruken material by a linear material. Then we get this, this output displacement. Then we took on the first line, we change the finite element solution in the material linear solution. The material linear. Here we change and we obtain this. There is no difference between these two kinds, but there is a huge difference between the nonlinear topology when a stress constraint is present and a lot of elements are active in the final design, in the optimized design. It's very interesting as a conclusion because the main reason of using a polyconvex model in non-stress-based optimization problems is that the Nehruken gives an extra stiffness to the mesh. So the Newton-Raphson scheme works well when for the stabilization. Okay, I'm finishing. I'm finishing. So it's interesting to note that the extra stiffness do not lock the complete mechanism, but the model is kinematically superior to the mechanism. Concluding, it's clear that the material nonlinearity assumption is not effective for problems that do not take stress, as I showed to you in the first example, but the second example shows that a polyconvex model plays a role that is not only to convergence stability, but to kinematic performance of the compliant mechanism as well. Okay, this is a huge investigation that's more explained in the full paper. That's the conclusion. Thank you, Emilio. I'm sorry for I passed some seconds, but that's it. Thank you.
Okay, thank you, Daniel. So I will open the floor for questions. Okay, so Oliver.
Thank you, Daniel, for your presentation. Very interesting. I have a question about the scalability of the approach, because you are using a p-norm function with p equal 8 to approximate the stresses, the maximum stresses. But what happens when you refine the mesh? Does it work, or how do you choose the right value for p as your mesh gets finer?
Actually, for this problem, we use 8 because a value larger than 8 didn't work very well for the stabilization problem, because the higher the p, the higher the non-linearity of the problem. So actually, we tried to use 12, but 12, especially when the stress constraint is active, the problem becomes hard to control because the p-norm of 12 is very nonlinear. But did you ask about refining the mesh? Yes?
Yes. Because the p-norm approximation becomes worse as the mesh gets finer. So I was wondering if like how you choose the right value for p if you have a finer mesh. Also, when you have a finer mesh, you have more numerical problems with element distortion because you're dealing with geometric nonlinearity. So how are you handling all of that?
Actually, for this research, it was a try and error scheme that we used. 8 was the highest number with no convergence problems where stress constraint is active. Actually, I did not perform a full investigation on the value for 8. A value of 8 worked very well. That's my explanation for this question.
Thank you.
Okay, so thank you, Daniel. I will stop here, and now I believe that we move to question and answer sections for all authors, right? And so if you have more questions for the authors, I believe Niels, you had a question for Liang Xia, right? So
I did, and I actually took the liberty to take it over the chat as we went along, so I already got my answer.
Okay,
yes.
Okay.
Thank you for remembering.
Okay, so if everybody, someone else has a question for one of the authors, so please, we have still some more minutes here, and so you can either ask in the chat or raise your hand. So. Okay, so I just have a question for you again, Daniel, since, so did you try to impose large forces in this model? Like I usually have problems with Newton Raphson when you push too hard the forces, right? So how it works, just curiosity, my curiosity here. So.
Yes, nice question, Emilio. Yes, I did impose larger force for, if I'm not making a mistake, I use 5 micronewtons. If I use 10 micronewtons, for example, we start to have convergence problem for the Newton-Raphson scheme. But with this force, 5 is a number that we impose a stress that is more or less the limit of the strength of the silicon, that the base material that we applied. So for larger force, we encounter some convergence errors, but these forces are very high on the strength of the silicon. So we believe that's not a problem, but yes, if you apply larger forces in this model, we have convergence problems. We cannot reach the convergence. Newton-Raphson scheme loses the path for convergence.
Okay, so Oliver, do you have one more question? So.
Yes, it's kind of a follow-up question of what you asked. Maybe the numerical instability can be because the elements are distorting a lot. I see that you're using simply a p-norm, I mean, a simple approximation for stiffness interpolation, but with geometric nonlinearities, the elements can deform a lot and even flip, and that will break down your numerical solution. So have you tried to use any of the established approaches like strain energy interpolation, interpolating between a strain energy of hyperelastic and elastic materials?
Yes. We observed some elements in the mesh near the hinges are becoming void, and then they are distortion excessively. So yes. I think another interpolation scheme we will find. Yes. Thanks for that advice.
Thank you.
Okay, so Jung, I think it's about to end, right? So it's 1:30 p.m., right? So I return the word to you. So thank all of you for your audience. Thank you, all the speakers for the presentations, okay? And thank you very much. Oh, okay, Niels, okay. You have a question, Niels? Sorry.
Oh, no, I'm just thanking everybody for being right on time. This is a commodity that's worth a lot of money. I mean, stopping at the exact minute. So I'm just applauding that.
Okay.
Thanks.
Yeah, I just want to thank everyone again for joining us, and thanks to all the speakers and also Emilio for organizing this session. And our next session will be on April 29th. It will be about topology optimization for manufacturability. It will be organized by Matthijs, and I'm looking forward to meeting all of you next month.
Okay.
Yes, please see you the 29th.
Okay.